So, Professor Langlands, firstly, we want to congratulate you for being awarded the Abel Prize for 2018. And you will receive the award tomorrow by His Majesty, the King of Norway. We would like to start asking you a question about aesthetics and beauty in mathematics. You gave a talk in 2010 at the University of Notre Dame in the US with the intriguing title, "Is There Beauty in Mathematical Theories?" The audience consisted mainly of philosophers, so non-mathematicians. The question can be expanded upon. Does one have to be a mathematician to appreciate the beauty of the proof of a major theorem, or to admire the edifice erected by mathematicians over thousands of years? Could you expand on this? What are your thoughts on this?
Well, that's a difficult question, Hart. At the level of Euclid, why not? I think in the article. The article was in a collection of essays on beauty. You will notice that I avoided that in the very first lines. I said, basically, I do not know what beauty is, and went on to other topics. And I discussed the difference between theories and theorems. And I think that my response is the same today. Beauty is not so clear. For me, it's not so clear that one should speak of beauty and mathematics at the same time. Mathematics has an attraction. You want to call it beauty, that's fine. But even if you say you want to compare it with the beauty of architecture, architectural beauty I think is different than mathematical beauty. So, unfortunately, as I say, I just avoided the question in the article, and if you forgive me, I'll avoid it today.
Yeah. As you are well aware of, Edvard Frankl, who you have worked with and who is going to give a talk on a couple of days from now on our lecture, talking about aspects of the Langlands program. He wrote a bestseller of a book with the title Art and Mathematics.
Yes.
And with the subtitle The Heart of Hidden Symmetry.
Yes.
And the Langlands program features prominently in that book. He makes a valiant effort, I would say, to try to explain to the layman what is the Langlands program. And I'm very intrigued also by the preface that Frankl writes. He says, there's a secret world out there, a hidden parallel universe of beauty and elegance, intricately intertwined with ours. It's the world of mathematics, and it's invisible to most of us. Do you have, you probably read the book, do you have any comments, further comments?
I've thumbed through the book, I have never read it. Now, I'm going to say something which is probably not relevant to your question, but there's something about which I've never thought. But, you know, we are scientists, we think about, and we listen at least to what scientists say, in particular about the history of the earth, the history of the creatures in it, history of the universe. And we even discuss sometimes the beginnings of the universe. But a question, something that puzzles me, I've never thought about it, except perhaps when I was taking a walk. But how did it start at all? It doesn't make any sense. You have to, either something came out of nothing, or there always was something, but somehow or other you have to, it seems to me that if I were a philosopher or you were a philosopher, we'd have to ask ourselves, how is it that something can be there? It's very complicated, but it's not so relevant that the world is very complicated. It's simply the fact that it is there. And how did something come of nothing? Well, you might think maybe with numbers it can happen. Huh? But beyond that, I don't know.
But you have had your creative moments where all of a sudden you have had a revelation.
Yes.
And hasn't that been a feeling of immense beauty before you? Or
When suddenly things fit together?
exactly.
Not quite like looking at the clouds or looking at the sea or looking at a child. It's something else. It just works. Suddenly it works, and it didn't work before. It's very pleasant, but your theories have to be structural. I mean, there has to be something, some structural, some appealing structure in a theory. But you know, beauty, women are beautiful, men are beautiful, children are beautiful, dogs are beautiful, and forests are beautiful, sky is beautiful, but numbers on the page or diagrams on the page, it's not quite the right word. And it's satisfying, it's intellectually satisfying that things fit together, but beauty, it's a pleasure when things fit together. As I said in the article, I avoided the word beauty, and because I don't know what it means to say that a mathematical theorem is beautiful. That it's elegant, it's gracious, that it's surprising, that I understand. But beauty?
But we can at least agree upon that Frenkel's endeavor, this book, was a valiant effort to really explain to the layman what beauty is in mathematics, and especially what the Langlands program is a beautiful thing.
Yes, I wish Frenkel were here so that I could present my views and he could present his. I read Frenkel and I studied Frenkel, but because he explained the geometric theory, so I wasn't interested so much in the beauty. I wanted to read his description of the geometric theory, and I got quite a bit from it. But I also had the feeling that it wasn't quite right. So if I wanted to say more, I would want to say it in front of him so he could contradict me.
Okay, we'll see how that works out.
So perhaps it seems like you agree with Tolkien, who said that beautiful was one of the ugliest words in English. So you have an intriguing background from British Columbia in Canada. And as I understand it, at school you had an almost total lack of academic ambition. Yeah, at least you say so. And so unlike very many other Abel laureates, mathematics meant nothing to you as a child?
Apart from the fact that I could add, subtract, and multiply very quickly. I did an interview in Vancouver, or it was actually, I was in New Jersey, but the interviewer was in Vancouver, and he asked me a question along those lines, and I didn't answer. I answered rather frivolously, but no, I told the experience I had with mathematics, of arithmetic. I mean, apart from elementary school and so on, I like to count and so on, was that I worked in my father's lumber yard, and those were the days when you piled everything on the truck by hand, and you tallied it, right? You counted the number of 2x4s. 2x4s, is that a concept here? 2x4s, 10 feet, 12 feet, 8 feet, 16 feet, and then you multiplied that, and then you added up the number of 10s multiplied by 10 plus the number of 12-foot lengths, you multiplied by 12 and so on and so forth, and you got a number and converted it to board feet or something, and then you knew how much it was worth. Now, the only experience I had with mathematics is that, of course, I would load the truck with some elderly carpenter or some elderly farmer from the vicinity, and he would have one of these small carpenter's pencils, and he would be very painfully marking 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and so on. And then he would have to add it all up. And of course I was 12 or 13 or 14, and I could tell him the answer before he even got started, and then I would wait patiently while he did that. So that was my only experience with mathematics, except for one or two tricks that you used in building window frames to guarantee that the angles are right angles. Well, that was just a trick, right? That the diagonals have to be of equal length if the rectangle is going to be right angled.
So why did you then move towards mathematics? No, why not language or other things that you studied?
Actually, when I went to university, in those days, that was almost the immediate post-war period. It was still regarded as necessary for a mathematician to learn several languages. So French, English, Russian, and maybe even Italian. Now that fascinated me. I had almost no, the instruction in French in Canada and English-speaking Canada was rather formal. Nobody paid too much attention to it, but that rather fascinated me, and the fascination has remained with me all my life. So that was incidental to mathematics.
Mm. But why did you start at the university at all?
Well, there are two things. I'll come to the second in just a minute. But so I went to high school. There were children from the neighborhood and from the surrounding countryside, and so they tested me. I was indifferent, so I didn't pay too much attention. But they also gave IQ tests, and my conjecture has always been that I had probably an unusually high IQ. I mean, quite unusually high IQ. I don't know. It didn't mean much to me, but that's my conjecture in retrospect. So we had, at the time, many of our teachers were just former members of the Army in World War II who were given a position as teachers, more or less in gratitude for their service in the Army. This fellow was young. He probably had a university degree, and he took once an hour of class time to say that I must absolutely go to the university. So I noticed that, but I noticed that for another reason, namely, I had acquired a mild interest in science because I had a book of my future father-in-law had a book about, it was a, so to speak, it was a rather leftist book about eminent scientists. So of course Marx was included, and Darwin was included, Einstein was included, and so on, various scientists from the 16th, 17th, 18th century, and he gave it to me. Now he had it, he himself had a childhood with basically no education, so he learned to read at age of about 37 during the Depression, when the labor parties were recruiting unemployed people, and so he learned to read, but never very well, and I think never really could write. But he had a good memory, so he remembered a number of things, and he also had a library, and in particular he had this book, which was a book that was very popular in pre-war. So I began to read in that book, and of course my future wife had more idea of what one might do as an adult than I did, and she did influence me. So I had that. So I had this book in which I read about standard people like Darwin and so on, and that influenced me a little. It gave me some idea of what one might do. And also there was the accident that I always wanted to leave school and hitchhike across the country, but I was when I turned 15, which was the legal age at which you could stop going to school, I had only 1 year left, and my mother made a great effort and persuaded me to stay another year. And during that last year, there was this. So things were changing for various reasons during that last year. The lecture of the English teacher, and the introduction to one or two books, and so I decided to go to university.
Yes, so you go on to have a master's thesis in British Columbia.
Yes.
You marry your wife, and then you go to Yale and start on a PhD.
Yeah.
So that's quite a journey that you're having there. How did you choose a thesis topic? Do you remember? For your PhD at Yale.
First of all, Einar Hille had a book. You may know Einar on semigroups, and I was an avid reader of that book. And I had a course from Felix Browder on differential equations. Now, Felix Browder, you may not know, but Felix Browder was an abysmal lecturer. And so you had to spend about 2 or 3 hours after every lecture. He knew what he was talking about, but it took him a long time to get to the point or to find, to remember this or that detail of a proof. So I went home and I wrote out everything he talked about, and so I had this background in partial differential equations from his course. I had all of Einar Hille's book on semigroups, and that I just put the two together. I would think about these things. In other words, I really like to think about these things. I thought about them. And,
so you found your own topic. You found your own PhD topic.
Yes.
Okay. Yeah.
But from there on, we have what I like to think of as a journey towards a discovery after your thesis. We have your work on Eisenstein series and so forth, working with the theory of Harish-Chandra and so forth. Would you care to explain to us what this background was before your advent onto the Langlands program on Eisenstein series?
There was an Hungarian fellow who had immigrated to the U.S. After the difficulties in Hungary. All right, so that was in the mid-50s. And of course, Selberg's wife was Hungarian. And so I think he was invited to the Institute by Selberg, he and his wife, and maybe their children too. So he had come into the U.S., sponsored more or less by Selberg, and then he was giving a graduate course at Yale. He talked about Selberg's paper. This was just basically at the time of Selberg's second, I think it was the second Indian paper. Selberg didn't write very many papers at that time, but I think there were 2. And he talked about that. So I began to talk, and also, I think I mentioned this as we were talking earlier, that there had been a promised seminar on convexity in the theory of functions of several complex variables. Well, if you hear about Selberg, you hear about Eisenstein series, and then you want to prove things. Well, this theory of convexity and you move instantly more or less to analytic continuation of Eisenstein series in several variables. So I'd already thought about that, but I thought about it in a rather restricted context. No algebraic numbers, for example. And then, so I went to Princeton, but not because of anything I had thought about Eisenstein series, but because of the work on one-parameter semigroups. So I gave a lecture in one seminar over which Bochner didn't run it, but he kept an eye on it. And I think he was impressed simply because I was talking about something that wasn't my thesis, because I talked about this work with Eisenstein series. So I think he was impressed by me. And then Bochner was someone who had, of course, his family was in Berlin, not that when he was born, but when he was a child, he went to universities, and he had connections with Emmy Noether and Hasse, for example. So he took an interest in anything that had to do with algebraic number theory. So he encouraged me to think about Eisenstein series in a more general context, not for, say, groups over over the rational number, but for groups over algebraic number fields.
So Bochner was almost like a mentor for you for a while?
Not a mentor, but Bochner was like a foster father, if you like. So he encouraged me. It was more an encouragement. He sort of pushed me. Maybe I had already mentioned this once to somebody else today, I think. In other words, Bochner, so he encouraged me to work over algebraic number theory, or number fields rather than just over the rational number field. So algebraic number field, I basically learned from Hecke, and I read papers by Siegel, because there are ways of analytically continue theories that you could take from Siegel's papers, Carl Ludwig Siegel. And so I started to read a bit in the literature of these two, Hasse and Siegel, and write about Eisenstein's theories, basically using these very classical methods. In any case, one year, just about a week before classes were to start, I had given no thought to class field theory. And Artin had been in Princeton, had been a specialist on class field theory, but he had gone away back to Germany. And there were one or two disappointed students who had come with him to learn a little bit about class field theory, but there was no real information to be obtained from the courses on class field theory. And I came back a week before, and so I knew nothing about it. I attended a seminar arranged by these disappointed students, but it wasn't such a good seminar. So I was quite innocent. And Bochner said, it was a week before, Bochner said, you're going to give a course on class field theory. I said, how can I do it? I don't know anything about it, and there's only a week left. Well, he insisted. So I gave a course on class field theory from Chevrolet's paper, which is a more modern view, and well, I got through it. With 3 or 4 students who said that they learned something from it. So that I began to think about the fact that, I was aware of the fact that there was no non-abelian class field theory, and that some people like Artin didn't expect there to be any. And so I was just aware of it, that's all. It was, and so that was that. I don't know, we're probably working in 64 or something like that.
Oh, that late already, okay.
Yes, that late. I could go back and decide whether 64 or 65.
And you already had a position at Princeton at the time?
Yes, that was all that time, except for I took a year. I was at the Institute, thanks to Selberg, I was at the Institute for a year, and I was in California.
Okay.
So I was away two times. So I had a comfortable position at the university. I went up the ladder of reasonably rapidly. I think by 67 I was maybe an associate professor, something like that.
And all this while you were doing this, you were contemplating on the trace formula. Is that correct, or?
Well, let me go back.
Oh, yeah.
So I've forgotten something. So I was concerned with the trace formula, and I wanted to apply it. The obvious thing when you want to apply the trace formula is to calculate the dimension of the space of automorphic forms. That's the simplest thing. So I wanted to do it, and so you plug in a matrix coefficient of that I understood, but it doesn't look like a matrix coefficient of an infinite dimensional representation into the trace formula, and you calculate. I didn't know quite what to do with this. And then I spoke to someone, he died very young, David Laudenslager, and he said, well, people are saying that there's something to be found in Harish-Chandra. So I started to read Harish-Chandra, and what I observed very quickly, because of reading Harish-Chandra, was that this integral that was appearing in the trace formula was an orbital integral of a matrix coefficient. And the orbital integral of a matrix coefficient, we know from theory of representation of finite groups, is a character. So, and basically you learn from Harish-Chandra's paper that this is the case. So that meant that I had to start to read Harish Chandra, as I did. And once you start to read Harish Chandra, it goes on and on. But that was the crucial stage, this observation of Laudenschlager, that people are beginning to think that Harish Chandra is relevant. All right? So there we are, we have it all. And so I began to think of all these things slowly, and sometimes it worked out, sometimes they didn't. This work, I could calculate, I could apply the trace formula successfully, but that's ultimately neither here nor there. So the dates are a little obscure, right? Because when was the International Congress? Early 60s, 62 or 64?
62 was in Stockholm.
All right. So the year after, so Gelfand gave a talk the year after at that conference, and a year later his talk was circulating. Now he gave his views of the matter. The point was that he introduced the notion of Kussform explicitly. Kussform is a critical notion, and it's a notion that I think appears in rather obscure papers of Harish Chandra and Gautam. But it's hard to, you have to look for it. But with Gelfand, it was clear why that was so fundamental. Now, the question, as an incidental question, I don't think Selberg ever grasped the notion of, Selberg of course didn't read other people's papers, and I don't think he ever grasped the notion of Kussform, and I think that was an obstacle that he never overcame. But as soon as basically once you read Gelfand, you could do it. You could prove the general theory of Eisenstein series. You had to know something. In other words, you had to be someone who knew about operators, unbounded operators in Hilbert space. So you had to have someone with this kind of background, or it didn't mean anything to you. But if you had that background, then you saw immediately what was to be done. And so take what Selberg had done in rank 1 to the general case. I only talked really mathematics with Selberg once in my life. That was before I came to the Institute, was at university. He invited me, at Bachner's instigation, I'm sure. He invited me over and he explained to me the proof of the analytic continuation in rank 1. Now, of course, the proof of analytic continuation in rank 1 is just the theory, it's like Hermann Weyl's theory of differential equations of second order on a half line. If you know, I'd read Coddington and Levinson not too long before, so I could just sit there and listen to Selberg. This is the kind of thing he knew very well, and he explained it to me. Whether he regretted that afterwards, I can't say, but he explained to me how it worked in rank 1.
Were you impressed by his presentation, or what?
I had never spoken mathematics with a mathematician at that level before in my life. I had never really spoken with mathematics with Bachner. And he's the one who would.
And what impression did he make on you? What impression?
As I say, he was the best. He was clearly the best mathematician with whom I'd ever spoken in my life up until that date. That's what.
But even so, you didn't have further conversations with him afterwards.
No, he wasn't a talkative man, you see, what I did have occasional conversation, because then I would. Still continuing to try to prove the fundamental analytic continuation of Eisenstein's theories. That comes a little early enough when I would say to him, well, I've done it in this or that case. Well, he would say, well, we don't care about one case or that case. We want to do the general theory. So he didn't listen to me. I never really, although I was a colleague and offices were basically side by side, we would say hello, but that's about it.
May I interject here, because you came to the Institute of Advanced Study in 72, I gather? 72?
Yes.
Yeah, and you had the office that Albert Einstein used to have.
Well, yeah, we have to be careful about that. First of all, that was not in 72.
Okay.
The office was occupied before me by Björling.
Oh, Björling had it before you. Okay. But anyway, and Selberg was virtually adjacent office, the one that von Neumann used to have before.
Yeah, I don't know about
Yeah,
von
yeah,
Neumann
yeah, right,
before my
yeah.
time. It was-
But anyway, it's sort of interesting. You spent time together a lot of years, and you never spoke mathematics at the time with
no,
each other.
Selber, you must know, didn't speak with very many people about mathematics. And he spoke with one or two, I think, but not many. And I'm not sure how much he thought about mathematics in his later years. I just don't know.
But even so, this work of yours on Eisenstein series, it really had some consequences in hindsight, didn't it?
Yeah, so it was critical in hindsight, right? Because, so that took me about a whole year. And I think I was exhausted after that. It was one of the cases where you think you have it. There was, for example, an induction proof, and induction proofs that you have to know what to assume, and if you assume too much, it's not true, and if you assume too little, then it doesn't work. So it took me, and in fact, there was a problem. In other words, things were happening that I didn't recognize. Something could happen, in other words, there could be a second order pole where you naturally assume there was only a first order pole. And then, so I thought of, so it took me a long time to reach that stage. In other words, it's for G2, it's for the group G2, and you think this is going to work, and then you try it and it doesn't work. Somehow it doesn't work in general, and then you think about it, where could it really go wrong? And it turns out you only go wrong for G2. So you make a calculation for G2, and and what do you see? You see there's a second order pole, or a new kind of first order pole. And so that changes the game. You have a different kind of automorphic form. But it eventually worked. It was an exhausting year, and it eventually worked.
But then you went to Berkeley, is that correct?
Then I went to Berkeley, pretty much exhausted from this particular adventure. And
Were you really so, let's say, exhausted that you thought really about quitting mathematics?
But quitting mathematics is a strong statement, right? So, but I did decide. I spent a year in Berkeley, and I got some things done. In retrospect, I had done more than I thought I had done. I was too demanding. You're young, you're a little more demanding than when you're older. So then the next year, I was really trying to, I think, to do something with class field theory, and I didn't see anything. I had a whole year in which I don't feel it. Berkeley, I did something in retrospect, but the year afterwards, I didn't at first do anything, and I was growing discouraged. So I decided a little bit of foreign adventure, so I pretty much decided that the time was I should just go away and maybe think of doing something else. Well, this opportunity, I had a friend, a Turkish friend, and he explained to me the possibilities of going to Turkey. So I decided to do that. So deciding to do that, there were various things to do. I wanted to learn some Turkish, and then I wanted to, I went back to studying Russian. I had a very nice teacher, but I still had a little bit of time to spare, and I didn't know quite what to do. And I began to calculate the constant term of Eisenstein series.
Just for the fun of it?
Just for something to do. And so I calculated them, and so you'll be doing it. And I began to, so I looked at it, and I just calculated it for various groups, and then I noticed that it was always of the form basically f of x over f of x plus 1, something like that. Mm-hmm. So, but if you can continue the Eisenstein series, then you can continue the constant term, and if it's f of x over f of x plus 1, then you can continue f of x. And these things are Euler products. Right? So you have new Euler products. And that's, of course, analytic number theorists just loved Euler products. So you had it. You had something brand new. They had an analytic continuation, functional equation. So there you were. You had something brand new, and you could do basically you could do one of these for every group of well, you could just do it for a lot of groups. Every Cartan class had.
Even reductive groups. You could even do it over reductive groups.
Well, you basically did it for split groups, so according to, and then you have the classification, right? And then, so you had a whole bunch, right? And if you looked at them, you could see that somehow they were related to a representation of. So Eisenstein theory is associated with a parabolic group of rank 1, and they were somehow related to a representation. You take the reductive, you have a parabolic group, you take the reductive subgroup, which is a rank 1, and then you have you throw away the rank 1 part, and you have basically some kind of L function associated to the automorphic form on this reductive subgroup. So what you have is you have Euler products that are attached to a representation of a group, so Euler products these are the Dirichlet series that number theorists love, and that's what you want. You want to sum. So you had these, and for each group, basically, or you had a large list of groups, and so that already suggests something. And then you begin to form. You can say you can formulate this. You can see somehow where this is coming from. You can see how to formulate it as a representation associated to an automorphic form, and a representation, a particular representation of what I call the L group for L series. And so there you were. Then you start to make a guess. You have this in general. Now I've got, for a particular reductive group, I have an Euler product with an analytic continuation associated to a definite representation, but you're thinking, well, maybe it works in general. So once you have that, once you have something that might work in general, you think about how you're going to prove it.
But this must have been extremely exciting.
Well, it was.
Yeah. And what about, did you continue your class in Russian or Turkish, or did you?
No. I tell you, suddenly I gave up both, and as I said, the Russian teacher, who was a sweet woman, and I think she liked me because I was an industrious student.
But is it fair to say then that your discovery comes out of, well, you were extremely exhausted, you let your shoulders down, you play, and you have some evidence, and you have a discovery? Is that fair?
Yes.
So this comes through your exhaustion, and you're just playing with mathematics for a while.
Yes.
That is fascinating.
When did you get this, if you like, epiphany, where you saw the connection with the Artin conjecture and so on? I mean,
there was a Christmas vacation in the appropriate year, 1966, 67, yeah.
And this was before you sent the letter to André Weil?
No, the letter to André Weil, I mean, it's an accident. I wouldn't have normally sent a letter to André Weil. The point is that I went to a lecture, but it was by Chern, and they went to the same lecture, and we both arrived early. I knew him, but not particularly well. So we both arrived early, and the door was closed, and we couldn't go in. So he was standing there in front of the door. I was standing here in front of the door, and he wasn't saying anything, and I thought I should say something. So I started to talk about this business. And then he didn't understand anything, of course, and probably he behaved as you would behave under those circumstances. You also, this young fellow who's talking to him, he said, just as soon he went away, so he said, write me a letter. So he never read the letter, as far as I know.
But he had it written out, printed out. He had it typed, your letter.
He had it typed, that's right. Yeah.
This must have been a wonderful Christmas.
Well, no, I mean, I don't. Well, it's good to discover it, but you're young, you don't take these things so.
But you do tell a story where you had this well, just an epiphany where you saw the connection. You were standing in Fine Hall at the seminar room looking out the window.
Yes.
Can you tell us about that moment?
I was standing. I lived about. We had four children, and we lived about a few hundred yards away from. You know Princeton?
Yes, yes.
You know where Bank Street?
About, yes, yes.
You know University Place?
Yes, I do.
If you go up University Place, you cross the principal road, and then you go down a small lane. We were the third house on the left.
Okay,
And so I could easily walk to, that was not the new math building, but the old.
okay.
You know the old math building?
Yeah, yes.
It's a shame, but it used to be really beautiful.
Yeah,
They
yeah,
chopped
yeah,
it up.
yeah.
So I had an office. So you go in the front door, the president's garden was behind you,
Okay,
and you go in, and I had a small office on the right, and then there was a seminar room on the left. So I would normally work in the seminar room because the blackboard was bigger. And so I was standing there thinking, looking out the window, as one does when thinking, and then you could see it. So that's where it was, and that's why it was, because I was there one evening, probably while leaving my wife at home to put the children to bed.
that must have been a marvelous moment.
Yeah,
You
no,
saw-
I don't
you
think so.
saw
I
the
mean, I certainly was
connection.
happy, I can tell you that.
Yeah, yeah.
But
This is not the only moment you described where you're definitely not sitting by your desk and working. At another occasion, you tell that you're walking from here to there, and suddenly you see something. Is that a pattern of yours? Is that how you find things?
I have suddenly seen something very seldom in my life, so I don't think one can speak of a pattern.
Yeah, we talk about this Poincaré moment. You know, Poincaré when he entered the bus,
Yes?
and then all of a sudden he saw the solution to something he had been thinking about for months earlier, but had put aside, and then all of a sudden he saw the solution. So when I read about this story about when you saw the connection with the art in conjecture that you were doing, you know, which was contained in the paper that you, or the letter you wrote to Vi.
Except that somehow, in other words, I wasn't searching. I had no idea that I would stumble across an non-abelian class field theory.
Perhaps it's time that you actually tell us what the Langlands program is all about. Just in broad brush strokes.
The person with whom you talk, it seems to me. I think we discussed this a few minutes ago.
Yes,
We did.
Yeah.
We do it again.
Yes, we do.
As I said, I wish Ed Frankel were here, because after many years, I thought I would like to learn the geometric theory, and Frankel has many articles on the geometric theory, and I read them with care. They're quite pretty, and he explains them clearly. He explains the situation clearly, but as I say, so but when I read it, I was troubled by two things. First of all, they seem to be dealing with statements that they couldn't prove, and they just couldn't prove at all. It isn't that they couldn't prove them in general, they couldn't prove them in really specific cases.
But this is the geometric.
Geometric
But basically, the Langlands program as such.
Yes.
What is it about? What does it entail?
All right. So actually, I think I wrote, so to speak, something explaining that later. So you want to ask? We sort of know what the quadratic reciprocity law is, right? That two things that appear to be quite different are the same. Now, and we also know that, after V, one can define zeta functions, or L functions, if probably better, and you can define them over a finite field, and you can also define them. If you have a global field, you can take a product of the ones over a finite field, and you get some kind of L function associated to a variety, or even to, if you like, a particular degree of cohomology in the variety. And so you assume, presumably, one says a basic problem for arithmetic, for any kind of estimation of this number of solutions of Diophantine equations are these L functions that you can formally associate, and even in a half plane associate to the cohomology, or to a given degree of an algebraic of any kind of curve over a number field. So they're there. So the problem poses, presumably, if you could deal with these, then you can somehow or other, sometime or other, do more things about the estimation of number of solutions and nature of solutions and so on. I don't think, as far as I know, one has a very clear idea, except in very specific cases, what you could do with a knowledge of these L functions, global L functions, but they're there. So you will want to prove they have analytic continuation. So the only reasonable way, on the basis of evidence, is that they will be equal to automorphic L functions. All right? Now, from the point of view of the variety and the cohomology of the variety, you have Grothendieck formulated. I don't know to what extent he actually had a complete theory. I don't think he had the notion of a motif, and a motif had certain multiplicative properties and so on. So you had a whole family of functions which behaved in a natural functorial manner, and you wanted to prove that they could be analytically continued. But he managed to associate a group. In other words, these motifs were associated to a representation of a group whose nature had to be established. That aside, it was there. So you may not ever know its nature, but you should be able to find out its relation to other groups. All right. Now, on the other hand, what you would like, normally, to establish the analytic properties of these things, defined algebraic geometrically, you associate them to something that is defined analytically, because automorphic L functions, basically, at least, have analytic continuations. There's some question about it, right? Because you could do it for, if they're associated to GLN in the standard representation of GLN, that's the theorem of Jacquet and Godema. And then, so you need to do two things, which are more or less mixed, namely, for an automorphic form associated with a general group, you need to show that automorphic form really sits on GLN. You push it towards GLN, and then you define the L function. So it's not just an automorphic form, but an automorphic form that can be pushed towards GLN. Now, if you can, so that leads you to think, well, somehow an automorphic form is associated to a representation of a group, which has to be defined. In other words, there's a structure in the collection of all automorphic forms. You can pass them from one, they're associated with G. Now, it isn't true that if you're associated with the G, you can pass them to another group, G prime. If G goes to G prime, this is this so-called L group, whatever, and you have to push it forward. But if you have this motion, then you can push, you can say the automorphic form here is equal to 1 over here, and so the L function is the same. So if this one you take over here is GLN, well, then you know by Jacquet-Langlands that you can handle it. So if you have this kind of, so if you have a way of passing from whenever you have an automorphic form in one group to pass to other groups in the appropriate formalism, then you can handle the analytic continuation.
This is what you call functoriality.
Yes, this passing like that. So that means, if you can pass like that, that really means, if you think of what it means that you can describe it by representations of a group. And this is the same thing. This is something similar is happening over on the algebraic geometric side. And there's another group defined in a similar way. That's the Grothendieck and his motifs. So when you have the two, then you can do all the analytic continuation you want and get what you get is, of course, something for your great-grandchildren to discover.
But tell me, I mean, the Langlands program as such, I mean, as you described, and very
I mean, it's not a real program. I don't know that you...
yeah, but is it related in a way, I mean, philosophically, if you like, to the so-called Erlangen program that Klein introduced? Because
I don't think so. And
you don't think so?
I haven't looked at the Erlangen
because
program.
what Klein explains himself, of course, is that you should study geometries by looking at the groups that makes invariant groups of the things. But Klein described it also that this was sort of a leitmotif for his thinking. That,
Well, I would hesitate to use the word program, but I think that probably this leitmotif is right. And in other words, you have these two somewhat surprising structures on both sides, right? Groups, the groups moving from groups have the property that one goes to another, and you have it on the one side which is arithmetic, and the other side which is analytic or geometric, depending upon your point of view. So you move around, and you know that everything can go to GLN, huh? And so, and with GLN you have this one example of an Euler product that you can analytically continue. But I mean, if you listen to what I'm saying, I'm speaking out of a void, or into a void or something.
Yeah, but could you explain why is it important? This seems like a very naive question, and it is. Why is it so important to analytically or meromorphically continue this L function? Why is that so crucial?
Why is that so crucial?
Yeah.
That's a good question, right? And why is it so crucial to know anything about the zeta function? Where do you go? If you go to estimates and the number of solutions and things like that. I mean, what do you do with the information you have about the zeta function? And what would you do if you had all the possible information?
Okay, so
do you have an answer?
No, I don't.
I don't answer, but I think it's both cases it's that we haven't worked with in the right area.
Sure. Of course, we know that the classical zeta function tells you something about the prime numbers, distribution of prime numbers, etc. And of course, the Dirichlet thing does something with the arithmetic progressions and so on.
So you get that kind of information, but it's clear that that's what people are hoping for. You could ask, well, why do they want it? God only knows. So one is pushed, so to speak, by preconceptions in a certain sense, and you're trapped in the way you think mathematics should work.
Okay, but is it the other question I have is that you have the classical class field theory. I mean,
yes,
and of course that can be explained, or it is about. A Abelian extension of the number fields, and how primes sort of split, etc., etc., etc. And your program, or what's it called, the Langlands program, the generalization is often described as now you look at non-Abelian extensions of the number fields or function fields over finite.
Well, according to if you have V around. Then number fields means you're dealing with the question with an equation with a finite number of solutions. You're not dealing with the curve or variety. So I mean, but there's V zeta functions means that which are also can be put in there, mean that you're dealing with something about a one-dimensional variety, a two-dimensional variety, a three-dimensional variety, and so on. But you ask me, well, do you understand the implications of all that? And I will say no. One is speculating, one is hoping to prove rather small things in what is potentially an enormous thing, may be completely irrelevant. But that's what analytic number theory is about.
Andrew Wiles,
yes?
He said, and very openly said, that proving this modularity conjecture.
Yeah.
I mean, he was very much inspired by your philosophy, put it this way,
Yes.
to do that. Very, very much so. Could you expand on that a little?
He used a kind of, we're speaking about a specific kind of theory, right?
Yeah.
A theorem. And the specific theorem of this sort that he needed happens to be available by some sort of happenstance or some sort it's just a curiosity. The particular case of this general theory that I'm describing that is necessary for Wiles is there.
Okay, okay. But he said, I mean, that for him the Langlands program was sort of a guiding light, guiding to what you should look for. I mean, he.
Well, maybe so. You have to ask. That's the case for me, I guess, in some sense. But maybe you have to ask Wiles what he specifically meant, because I understood it to mean simply that he had this one case, which was enough for the Fermat theorem.
Okay.
I mean, there's one case of an Euler product that you could manage,
Okay.
because it was related to an Euler product someplace else.
But Wiles states it rather interestingly in one of the earlier interviews here that something like to the lines that the Taniyama-Shimura conjecture had to be resolved. So it's a problem. What he says, it's a problem in the middle of mathematics. You can't just go around it and forget about it. You could go around Fermat and just forget about it, and that's the end of it. But this problem was completely central, and it one day would be solved. So it's.
I don't know what the Shimura conjecture.
So the modularity.
Modularity conjecture.
Modularity theorem.
Yes.
That Wiles proved in order to prove, which led to Fermat. And he gives this sentiment that this part of the Langlands correspondence was of such a central importance that almost lent him courage, or this would have to be solved.
Uh-huh.
And is that something? So you propose a theory of mathematics that, in some sense, is rather encompassing, and it's not a particular thing, and it's a structural thing. Is that?
I think one is looking for a structural thing with all of whose particular instances are of interest. I think something like that. I mean, there's so much that one can't do that I hesitate to answer your question. But yeah, I mean, you have the one structure and the one from Diophantine equation, which is sort of bedded in one from automorphic forms. With the one in automorphic forms, you have a lot of, and it has a structure of its own, and so you have a lot of information about the L functions here, and they move back here, and that more or less, usually that does what you want, I think. But I'm not a specialist about those things.
Let's move on. I mean, this so-called fundamental lemma that
Yes.
was proved by Ngo, and he got the Fields Medal for it in 2010. And actually, Time magazine said that this was one of the most important discoveries in 2009.
You can cancel your subscription to
Yeah.
Time magazine.
But sure. But the point is that this, I heard that this, because the lack of a proof of the fundamental lemma kept the theory, the Langlands program, back 20 years or something like that. Because okay.
No.
Okay.
The fundamental lemma is inserted to deal with specific kind of technical question. Right? This is not a good example, but I want to. I'll try to explain something. Right? Suppose you have something like group SLN,
Okay.
and you have SUN. Right? So you know about, after Wiles' theory or something, you know about the representations of SUN. Right? I mean, those are basically the standard finite dimensional representations of this group. Now, if you look at the SLN situation, what happens is, so the SLN has more representations than SUN.
Yeah.
I mean, SUN is a certain form of, it has less than SLN. But in addition, over in SLN, you have, so SLN has a lot, is a non-compact group, it has a lot of representation, but in particular it has some things which are very much like those of SUN, in other words, the characters are basically the same. You know the character, I mean, let's take SU2, it's each of the IN theta minus each of the minus I over each of the, and now let's go over to SLN. It has, for the Harris-Chandler theory, I mean, which, for SL2, that it's previous to Harris-Chandler, you have corresponding representations. In other words, in this whole theory of representations of semi-simple groups or simple or reductive groups, and therefore in the theory of automorphic forms, and therefore in the whole theory, what happens is that for SL2, those things where there's only one, I mean, you know there's one, SU2 there's one representation in each dimension. Yeah. But so each one has basically something corresponding over for SL2, so-called discrete series. But the discrete series, it has, at each end it has two. And it's just this one thing which is only one for the unitary group becomes two at SL2. All right? Now, but these two are for all practical purposes the same. They're just two pieces. Now, this fundamental lemma occurs because then what you have to do, if you're worrying about the trace formula, you want some part which is a really useful part for, say, SL2, and that's the part where you put these two together, as so they look like SU2. And then there's a supplementary part where you have to take account of the fact that they're not really, they don't occur with the same multiplicity. So you have this extra stuff. So if you want to do handle the trace formula, you have to, say you want to compare, you want to say SU2 is more or less like SL2. So you compare the trace formula on the true, yeah. But this extra bit over here is causing you trouble. Yeah. So that is, so, and the reason is that somehow the one representation here breaks up into two here, and some of it is really, so to speak, it doesn't have much to do with things. It's just there. You just take the difference of the characters rather than the sum. And you have, if you're going to use the trace form or anything else, you have to understand that part that you don't really want. All right, and so there's something, the theory of endoscopy, and what's so-called fundamental lemma was a fundamental lemma in the context of the specialized theory which you introduce for this special. For this special factor, that things which, so to speak, should be the same can sometimes differ. So you have to, what you do is you treat them as though they're the same, put them together, and then you take the difference, and then you have to look and treat those differences separately. They look like something coming from the torus itself, the circle group that sits in there. So it's a technical necessity. Namely, if you want to compare the representation of two groups, you use the trace formula. But this stuff, this extra stuff, you have to get it out. You have to set it aside and treat it separately so you can compare what's left. And so what matters is it's just to understand what you can't compare on its own. And that means you have to understand the differences. So you have to look at the circle group, which is all that matters. And for that, you need the fundamental lemma. So the fundamental lemma is the fundamental lemma for these technical purposes, and all that. So don't believe what you read.
Okay.
I mean, it was hard to prove, but it's not, so to speak, fundamental.
I see. But the fundamental lemma takes care of exactly that problem. I mean,
yes,
solve that. Okay.
There's a whole theory for it because it's rather complex, but it takes care of that.
But you say also after the fundamental lemma, you say that for the functoriality thing, which is the important part of the Langlands program, I mean this functoriality question, that the key you surmise that the key to making progress is the trace formula in the stable form of Arthur Could you explain something about why why you think the trace formula is so crucial?
Yeah, well, what do you want to show? Right? You want to show that I can transfer everything to GLN, basically.
Okay.
Or no, let's put it somewhat differently. You want to show that I can move automorphic forms from one group to another.
Okay.
So that means somehow you do want the trace formula. You compare the two trace formulas, right?
Because you say something that, of course, functoriality is such an important, the most important part of the Langhans program. And to make progress, you say that you think that the crucial tool is going to be the trace formula in the Arthur sort of stable form.
Yes. All right.
And I just want to know, why is the trace formula is going to be so important?
What you want to do is, you see, if you have G and G prime, you want to be able to move things from the group G to the group G prime. You want to be able, in particular, to handle the L function, so you want to be able to move them to GLN.
Right.
So, and I say these things work at the level of the L group, but let's just work with GLN or something.
Okay, sure.
So we don't have to worry about that. So how are you going to do it? To what you want to do is somehow you want to, you can pretend you know. You can pretend in principle you know. In other words, you say, here's this group. Every time I have a homomorphism of the group, really the L group, one and the other, then I have a transfer of representations. All right? So that means that every representation is obtained by transfer. It, so to speak, there's a natural transfer, because you can see this when you see the distribution, so to speak, of conjugacy classes. So what would you do? Right? You would. So there's, so to speak, a smallest place, a smallest group where it sits, and then it's propagated to the other groups. Huh? So for example, so if you have this one group G, you want to understand it, right? So you say, well, here's a smaller group, so there has to be the contribution of those things which sort of sit in the bigger group, that's that smaller group. So one away. You do it all along, and you look at the trace formula here, you look at the trace formula here, and they cancel. In other words, if it comes from one place, you look to see what it cancels. It cancels something, and you go along and along and along when you understand it, and then ultimately, the real building block is those things on the big group, which come from the trivial group.
Right.
So and then that, so to speak, the last stage is to analyze those. So you can look and see, well, how do I take the small group and I want to send it to the big group, and I just have to look. I take the trace formula up here. It cancels everything I know from these. It just cancels everything. I said it should be made up of pieces, and each should come from some smaller group. So I just say, well, this comes from the smaller group, this comes from the smaller group, this comes, and then I have to be careful, because they could come from a bigger group and a smaller group, and I have to be careful I don't count it twice. So I said this was this, and it should be so that they should be equal. I have to have a clear view of the combinatorics. Right? So I have a clear view of the everything comes from a smaller group. Some of it comes from two things in a smaller group. Some of it comes three, and so on. And this depends upon the image group. But so to show that this is really true, I just show that somehow that the trace formula gives the same up here as it does for something collection from the various groups. This is pretty vague, but I think in principle it's not so bad.
Okay.
And that's how it works in fact, but up until now at a very low level.
Yeah. That's very interesting to hear. Yes.
I'm not so sure.
Yeah. But that so that is at the forefront of your investigation.
I mean, that's at the forefront of Arthur's investigation. I think if you want to hear the definitive or what's available along these lines, ask Arthur.
Okay.
But you're thinking in a more differential geometric line
Well,
now?
I was thinking, I've been thinking about the geometric theory, and the geometric theory is not the trace formula, right? The geometric theory is this basically this Yang-Mills theory.
And that was a recent release. That is a recent release of yours.
Yes,
So we can
I
read
don't know
up
if
on
it's really released, but it can be found on the web, yes.
Yeah, exactly.
Well, I guess we have to round up the interview more or less, but before we do that, I mean, you have this characterization of mathematicians. Sometimes you call them typically problem solvers, and then you have some that are, you know, form theories, mathematical theories. How would you describe yourself? Are you a theory builder, or are you a problem solver, or are you something in between?
Well, I think insofar as I'm anything at all, it's probably the first, right? You think of Fermat's theorem as a problem solved, right?
Right,
yeah,
right,
well,
right. Yes, yes. And in that vein, because you earlier in your career, you said that you admired Grothendieck and Harishchandra a lot.
Yes.
And was that because you saw them as, let's say, fantastic theory builders? Was that what impressed you with them, or was
Well,
it?
they certainly are, aren't they, both of them?
Yeah, so perhaps before we conclude completely the interview, it might be interesting to hear whether you have some non-mathematical private passions or interests of some sort: music, literature, language, or poetry, or...
I don't have passions, but you know, it is true that one would like to take a look at other things. You know, history is fascinating. You know, modern history, ancient history, the Earth's history, universe's history. These things are all fascinating, and it's a shame to go through one's whole life and not spend some time on them.
Contemplating on that.
Pardon?
Not to spend some time contemplating on that.
Yes. Or some, I mean, not everything, of course, but just to think about it a little bit.
Well, on behalf of the Norwegian Mathematical Society and the European Mathematical Society and the two of us, I'd like to thank you for a very interesting interview, and again congratulate you with the Abel Prize.
Well, thank you for the invitation.